Okay, I think we're good. So, let's start by talking about some average rate of change today. So, I'm going to put a little context to it this time. So let's say that we have just an equation this time. Okay, we've talked about it before with, like, I think the example we did was something about the average rate of change of like an object that is moving or whatever over time, that sort of thing. But in general, we should be able to do this process for just some function that we have, okay? So we're going to kind of change the context a little bit back into more just like pure math stuff here. So let's say that I have the function x squared minus 5x. And I want to know what is the average rate of change of f of x on the interval 1, 3. And keep in mind that a rate of change is simply a measure of slope. Okay? So it's a measure of slope from one point on the curve to another point on the curve. So if I were to graph this whole curve, I found the point on it at 1, I found a point on it at 3, I drew a line between the two of them, and I wanted to know its slope. Does that make sense? It's essentially what we're doing. Okay? So the average rate of change, if it's a slope, think about it like change in y over change in x. Okay, well the change in y is f of 3 minus f of 1. You plug in the 3, get a y value. You plug in the 1, get a y value. What's the difference? That's the change in that y. And then the change in the x is simply just 3 minus 1. So we end up with this f of minus f of on top, and then just the two numbers subtracted from the interval on the bottom. Okay, so then we got to do a little legwork of actually plugging the numbers in and seeing what we get. So f of 3, let's see if we can do that in our heads real quick here. 3 squared is 9 minus 5 times 3, that's 15. So 9 minus 15 is negative 6. And f of 1, 1 squared is 1 minus 5 times 1. So 1 minus 5, negative 4. So negative 6 minus negative 4 over 3 minus 1. So that's negative 6 plus 4, that's negative 2. 3 minus 1 is 2. So the average rate of change on that interval then would be negative 1. Okay? Or the slope of the secant line, we call it a secant line, is negative 1. Okay? So just to kind of illustrate here what we just did, just so you can kind of see it on a graph. So for this function, f of 1 we found was negative 4. Okay, so that was here. And then we had 3 was at negative 6. Okay, so this curve, I'm not exactly sure what this thing looks like. I mean, it's a parabola opening up. So it's probably doing something kind of like this. Not entirely sure precisely what it looks like, but something kind of like that. So it's curved, right? Well, what we just did was we said, okay, so yeah, if I got this little point that's going along this curve from 1 to 3, so I'm investigating just this little piece of it right here. So as that thing changes, what is its average rate of change, okay, with its position as it goes along there? So like I said, what we just did was we took these 2 points, connected them together with a little line segment, and we just figured out what the slope of that line segment is. Okay? So we found the slope of the secant line. It's called a secant line. So if you're asked to find the slope of the secant line or an average rate of change, you're doing the same thing. Okay? Now, usually we're not so interested in average rate of change. We're more interested in instantaneous rate of change, which we've looked at a little bit. An instantaneous rate of change would be taking these 2 endpoints of this interval and smashing them together at one point. So just at one specific point, what's happening? Okay? So we're going to repeat this process, but we're going to figure out what is the slope of the tangent line, or what is the instantaneous rate of change at, let's say, exactly 3. Okay? So same function, kind of a different goal this time, though. Okay, so what is the instantaneous rate of change, then, of f of x at x equals 3? So when we're talking instantaneous rate of change, remember that's at one specific spot. It's not over an interval anymore. Okay, it's not an average. It's exactly what is the rate of change at a specific spot. Okay, and we talked about that assume h was some kind of like teeny tiny increase in where we were at. Okay, and then we wanted that h essentially to be 0. And we came up with this limit definition here that said it's the limit as h goes to 0 of f of x plus h minus f of x divided by h. And we talked about how this has a special name. It's called a difference quotient. You don't really need to remember that per se. It's just, can you use it the right way? So for us, for this one then, what we want to do is we want to calculate the limit as h goes to 0 where x is 3, because we're interested in what's the instantaneous rate of change when x is equal to 3. So we're going to do f of 3 plus h minus f of 3 all divided by h. Okay, so we're going to do that limit calculation. So f of 3 plus h. All right, well, we've got to go to our function that we've got up top there and start plugging that stuff in. So that's going to be 3 plus h squared minus 5 times 3 plus h. Okay, so that all right there is my f of 3 plus h. And then I got to subtract from that f of 3. And f of 3, we've actually already done. We got what? Negative 6 for that, right? 9 minus 15? Yeah. So then this would be plus 6. All divided by h. And then we got to whip out our algebra skills here and multiply that stuff all out. Okay, so 3 plus h squared. Just going to start with that. So that's 9 plus 3 times h plus 3 times h, 6h plus h squared. And then distribute the negative 5, so minus 15 minus 5h, and then we've still got the plus 6 on there. All that divided by h. And then we can start canceling stuff out on there. So let's see. 9 minus 15 is negative 6 plus 6. So that's all. These are all essentially canceling out. And then we've got 6h minus 5h. So we've got the limit as h goes to 0 of h plus h squared. Still divided by h. So if we start canceling our h's there, then we've got the limit as h goes to 0 of 1 plus h. How did the what? The 9? What's 9 minus 15? Negative 6. Plus 6. So those are all gone. All right, so then I distributed that h, divided it out of both terms. So what's the answer now? What's the limit as h goes to 0 of 1 plus h? Just 1, right? Because you can plug it in now. So it's just 1. So what that means is at 3, we have a slope, an instantaneous slope of 1. So that tells us a little something about the curve at that particular point. So I'm going to come back to my little graph here. So remember, we've got this parabola-looking thing. So that means that when I'm at 3, which is maybe like here somewhere, here's my point. That means that that has a slope of 1. Well, how in the world can I show a slope when it's just 1 point? Okay, well, I have to have not a secant line like the last one, but a tangent line. So the line is still going to hit the curve, but it's only going to hit it at 1 point. That's what a tangent line does. And it has to have a slope of 1. So it's going to be something maybe kind of sort of like this. Okay. So do you guys see, like, if I had a bunch of tangent lines through here, that all my tangent lines at this point in the curve would be negative, or their slopes would be negative, right, as I'm coming down? And then as this thing starts to curve, these tangent lines start to level off. And then as soon as I come back up right here, now I've got a slope of 1 when I get to 3. Okay? So it's starting to head up. I had this really cool applet that showed you all this, but again, it didn't work, so I can't. But anyway, so that's kind of the idea, though, is that the instantaneous rate of change tells you something about a tangent line, the slope of the tangent line at that particular spot. Yeah?
When you were at the limit is 1 plus h,
Yeah.
what did you plug in to find 1?
0. Because we're doing the limit as h goes to 0. And the only reason I didn't plug in before that is because of the denominator, right? As soon as I cancel that, then I'm good to go. Yeah. Okay. So are we okay with that tangent line connection, though? That we're finding a slope of that tangent line at that particular spot when we do this? Okay. That's that kind of key connection from the graph to this whole calculation stuff that we're doing. Okay. Finding a slope of a tangent line. So you might be asked a question, what is the instantaneous rate of change at a particular spot? Or you might be asked, what is the slope of the tangent line at a specific spot? Okay? It means the same thing. Just like finding the slope of a secant and doing the average rate of change is the same thing. Doing an instantaneous rate of change and the tangent line, that's the same thing too. Okay? So, I'm going to have you guys do one of these for me. And then if we're good there, then we'll move on to finding the equations of tangents and normals and all that, and then we'll be done. All right, so let's see if we can do this. What is the slope of the line tangent to f of x equals 3x minus 2x squared. Jeez, really? At, let's do x equals 0. Okay, so to answer this question then, I got to do that whole limit business again with h, right? So we're going to do the limit as h approaches 0 of f of, so in this case, because I want it when x is equal to 0, it's going to be 0 plus h minus f of 0 all over h. Okay, so let's start plugging some stuff in. This is going to be essentially then just f of h, right? So we've got the limit as h approaches 0. F of h would be 3h minus 2h squared. And then what's f of 0 for this? It's not meant to be a difficult question. What's f of 0? 0, right? Okay, so minus 0 all divided by h. Alright, so we simplify and all of that. Limit as h goes to 0 of 3h minus 2h squared over h. You guys all see how that's going to cancel now with the h's again? Okay, each term's going to lose an h. So limit as h goes to 0 of 3 minus 2h. Now that I have things canceled, what's my answer? 3. So on that particular graph, at x equals 0, we should have a tangent line that has a slope of 3. Okay? So answer me this. This is something we'll talk more about later, though. At x equals 0, is the graph increasing or decreasing? How do you know? It's a positive slope, right? If the tangent line would have had a negative slope, it would be decreasing at that spot, right? And if the tangent line has a positive slope, it means you're increasing at that point. So this instantaneous rate of change business is going to open up a lot of doors for us in some things that we can say about functions. See if you can answer me this then. What would you expect the slope of the tangent line to be at a maximum or a minimum of a function? 0. That's going to be a huge connection we're going to talk about in the next chapter. Is if we know that the slope of that tangent is 0, then we can identify maxes and mins. In pre-calc, we talked about maxes and mins. We were never able to calculate those things by hand. We always had to look on a calculator to do it. Now you guys have the means to do it by hand. You can figure out where all the maxes and mins are of a function simply by knowing that if you can get the tangent line slope, you should be looking at 0 for each one of those. Okay, and that's something else we're going to do with this later on too. So, okay, so I think we're good with that. So now, can we take it a step further, and can we actually come up with the entire equation of that tangent line? Because it's a line, right? And all lines have equations. So let's see if we can do it. So if we have some curve, okay, and let's say we're looking for the tangent at this particular point right here. We'll call it A. And our tangent line is doing something like this. Okay, and I want to find the equation of that line. Well, we've already found out, or we've already talked about a method to find one piece of information about that line. Its slope, right? So we just discussed the slope of this is the instantaneous rate of change. And what else do we really know about that line that we can use to help make an equation for it? Think about the very first section we studied in this class. It was all about lines, right? What do we need to make an equation of a line? If we could use a y-intercept with slope. That's one way, but we don't have a y-intercept, so we're kind of stuck there. What else could we use? A point. Didn't we do that, right? If we had a slope and a point, that was enough, right, to make an equation of a line? We have that, don't we? Where's the point? Right there. Okay? So our point we're going to use is a f of a. Okay, we got to plug in a to get the y, but yeah, so a f of a. So we got a slope, we got a point. Good enough, we can do it. We can go back to those techniques we talked about before. So let's try that. See if we can do it here. So what is the equation of the line tangent to f of x? So we'll just keep it simple for this one. How about just x squared? And we'll do it at x equals 1. All right, so unfortunately, we do have to do all of this instantaneous rate of change limit as h goes to 0 stuff every time we do this, because that's how we're going to get the slope. But after we've got that, then it's pretty straightforward. So we're going to do f of 1 plus h minus f of 1 over h this time, right? Because we're finding it at x equals 1, so 1 plus h and 1. All right, so 1 plus h squared is 1 plus 2h plus h squared. And then f of 1, well, what's f of 1? 1, okay. Are you guys to the point now where you could do the next two steps in your head? We've done enough of these, or maybe you can start doing that. See if you can follow me here. 1's will cancel, h's then will cancel. I'm left with 2 plus h. Right? 1 minus 1, those are gone. Cancel out h's, and we get 2 plus h. So what's the slope? 2. All right, so slope of our line is 2. And a point that it goes through. Well, we were looking at x equals 1. So 1, what's f of 1? That's the y-coordinate of this point. What's f of 1? 1. So we need to make a line that has a slope of 2 and goes through the point 1, 1. So y equals 2x plus b. Now, if you like point slope form, by all means, you can do that too. This is just the way I think most of you guys did it. So we can take the 1 and the 1, x, y, plug them in. 1 equals 2 times 1 plus b. So b equals, what, 1 minus 2, so negative 1. So the equation of our tangent line is y equals 2x minus 1. Okay, and the only other thing I really need to go over with you guys, and then I think I'm good to go here with you, is a normal line. Now, depending on the context, and we'll get to some application stuff like in Chapter 4 where we'll talk a lot about this, but there are some instances where we want to know what's the equation of a normal line. Well, we need to talk a little bit about what a normal line is. Any of you guys in physics? You guys know what the normal force is? What is a normal force? A force that is perpendicular to the plane, right? So a normal line rather than being tangent to the curve, it's perpendicular to the curve. Okay? So if we had a little function going along here, let's say I wanted to find the normal at this particular point right here, what I would do to sketch that here, here's your tangent line. And so the normal line would simply be perpendicular to that line through that point. Okay? So the normal would go something kind of like this. So this one is the tangent, and this one is the normal. What is the only thing that's going to change about this process if I want to find the equation of a normal line? Yeah, exactly. The slope's going to change, right? It's going to be the negative reciprocal of whatever the tangent was, and then continue. So you still got to do that difference quotient. You still got to do that limit as h goes to 0, etc., etc., etc. Do that process out, but then take your answer and change it. Make it a negative reciprocal, and then continue on. So to save a little bit of time here, let's go back to the last example, except just change the directions and make it normal line instead of tangent line. Okay? Because we've already done the hard work of figuring out the slope of the tangent. Okay? Our tangent slope we already found was 2. If the tangent slope is 2, what's the normal slope? Negative 1/2. Good. And again, don't we still have a point it goes through, right? The tangent and the normal both go through that same point. So we use the point 1, 1 in getting the equation of the tangent, so let's use the point 1, 1 again to find the slope of, or to find the equation of the normal. So we're looking at an m of negative 1/2 of point 1, 1, okay? So y equals negative 1/2 x plus b. So if we plug in the 1, 1, 1 equals negative 1/2 plus b. So b equals, if I add a half to 1, that's 3/2. So my normal equation then is y equals negative 1/2 x plus 3/2. So I can do that too. I can figure out the equation of that normal. All right. Any questions about any of this stuff, guys? Yeah. How did I get the 3/2? I have to add 1/2 to the other side, though. So, all right. So to recap a little bit with you, the kind of the big concept: average rate of change, slope of secant line, same thing. Instantaneous rate of change, slope of tangent line, same thing. Okay. The rest of it is just working with linear equations like we've done in the past. So, all right. I'm gonna let you guys get to it here.